Today we're going to talk about another method for approximating the area under a curve. Now, last time we did it using rectangles, both from the left, the right, and midpoints of the subintervals. But this time we're going to use a method that's going to be a bit more accurate. We're going to use trapezoids. So what we're going to first do before we get started with anything is we're going to call A, the starting point of our interval, x naught. And then we're going to label each of these as x1, x2, x3, and so on. So I get down to here where B is x sub n, and the one before is x sub n minus 1, and so on, going back until we get to the beginning again. And this is going to help us to develop a formula here in a minute for the area under a curve with a trapezoidal approximation. And so what we're going to do then now is we're going to say that we have divided this interval from A to B into n subintervals. Now there's two cases again here. One where the subintervals are all equal, and one case where the subintervals might not be. So we're going to take both cases into account here. But before we do either of those, we have to actually draw the trapezoid. So what we'll do is we will start at x naught, and we'll go up to our function up here at x equals x naught. And we'll also do the same at x1, just straight vertically up. And then we will connect the points where those vertical lines touch our function. And now if you look at it kind of on its side, we've got a trapezoid with one base stretching from x naught up to this point up here, which we'll call y naught, and the other one stretching up here to a point that we'll call y1. And those are the two bases with a length of y naught and a length of y1. And our height is the distance between x naught and x1. And if we remember back to find the area of a trapezoid, the area of a trapezoid is base 1 plus base 2 divided by 2, in other words, the average of the two bases, times the height. So in order to find the area of this first trapezoid, we would do base 1, so y naught, plus base 2, y1, divided by 2, times that height value. And for our purposes right now, we'll call this h1. Okay? And then we do the same thing again with the next trapezoid. So we draw a line straight up here, and we'd connect that to right there. This would have a height of, we'll call it h2. And this height up here is just a height of y2. And so our next trapezoid would be y1 plus y2 divided by 2 times h2. And we'll continue doing this over and over and over again. So here's one at x3, here's one at x4, x5, x6, x sub n minus 1, and finally over here at x sub n. And so as we go through here, we note that we get down to the end, and the last one here would be y sub n minus 1 plus y sub n over 2 times h sub n. And if you have unequal subintervals, in other words, if the value of h, h1, h2, h sub n, if that value is changing or different for any of the intervals, all you can do is find the area of each trapezoid, add them together, and get your answer. But if we were to take the case where these are equal subintervals, we can now go through and we can eliminate the 1 on the h, the 2 on the h, the n on the h. Right? We don't have to worry about those anymore because those heights aren't changing. So I'll erase those down there. And now we'll note that this trapezoidal sum, when we have equal subintervals, will come out to be h. There we go. H over 2, because each of these terms had an h over 2 in it, times Well, we've got y naught plus a y1 and plus another y1. So that'd be 2y1. And then we'll note that we have a y2 here. And then this next term that I've left out with my dot, dot, dot is also going to have a y2 because both this trapezoid and this trapezoid share the length of y2 here between them as a base. And so we're going to get y2 in here twice. And we're going to get y3 in here twice. And y4 and so on. And we're going to get 2y sub n minus 1s because down here, this is y sub n minus 1. It's used for this trapezoid and this trapezoid. But at the end, we only use y sub n once. And so this is our generic formula when the value of h is always the same to approximate the area under a curve using a trapezoid. And we'll note that the value of h, when we have equal subintervals, should be the length of the entire interval, b minus a, divided by the number of subintervals, which was n. So that's how we'll get our value for h. H will be b minus a over n. Now, a few other things that we're going to note here really quickly is that when our function was concave down, as in on this interval right here, we can see that that trapezoid is underestimating the true value of the function. And when our function is concave up, like it is right here, our trapezoid is going outside the function. And so we're overestimating it. So I'll have a slide that has that down. But here's our formula. Right? The sum of all the trapezoids, or the area under a curve using a trapezoidal approximation, is just h over 2 times y naught plus 2y1 plus 2y2, and so on, until we get to 2y sub n minus 1, and then a singular y sub n at the end. And it's very important that we note that h is b minus a over n. And so that's the formula that we've just developed. We're going to use it once in a second here. I'll note also that a trapezoidal approximation here is the average of the left and right endpoint approximation. So it's the average of the left Riemann sum and the right Riemann sum. And in some cases on the AP test, most likely when they just give you a chart of values, sometimes you won't be able to have equal subintervals. So in that case, you can't use the formula here. You just have to take the regular trapezoid area formula that we talked about on the previous page, and we have to use that repeatedly until we find the area of each of those trapezoids. Sum them all together. And the last thing before we do a problem here is what we talked about the concavity. The function is strictly concave up, and we're trying to use trapezoids to estimate this area. I'll just draw a couple of them in here. We would note that on a place where it's concave up, we are clearly going over, and this is an overestimate. And concave up is an overestimate. And if we flip that around and have a function that is concave down, and I'm trying to approximate this area here using trapezoids, we're going to be underneath that curve. Concave down is going to give us an underestimate. So that's about all there is to it. We'll use this rule once here to see if we can approximate the area under f of x equals x squared on the interval from 1 to 5. And it says we're going to use 4 equal subintervals. So if we're talking about 4 equal subintervals from 1 to 5, well, first off, we'll need to figure out what our value for h is. And h is b, which is 5, the end of our interval, minus a, the beginning of our interval, 1, over n, the number of subintervals, which is 4, which tells us that h, the length of each subinterval, must be 1. Well, if the length of each subinterval is 1, the first one is going to be from 1 to 2. And then we'll have one from 2 to 3, 3 to 4, and 4 to 5. These are going to be our 4 little subintervals. And so now we'll just go in, since they're equal subintervals, we're allowed to use our formula. We'll say this area is approximately equal to h, which is 1 over 2, times y naught was our first thing in our formula. So y naught is just the function evaluated at its far left endpoint. Our far left endpoint is 1, and the function is x squared, so it'll be 1 squared. If our function was x cubed, it'd be 1 cubed. If our function was sine of x, it'd be sine of 1. And then now the next thing we have is 2 times y1. y1 is just our next subinterval endpoint, so that'd be 2. So x naught is 2, but y naught is 2 squared, again, because the function is x squared. And we'll have another 2 times the next x value squared, or 3 squared. And then we'll have 2 times the next one, 4 squared. And then the last one, of course, was y sub n, and that comes from x sub n, which is 5, the end of our interval. And that one doesn't get multiplied by 2. It just gets evaluated in our function as 5 squared. And we've now got half of 1 plus 8 plus 18 plus 32 plus 25. And it looks like if you add all that up, that's 84 divided by 2, which is just 42. And we could determine if this is an underestimate or an overestimate simply by looking at the concavity. We know that f prime of x is 2x, and f double prime of x then is just 2. Since 2 is positive, this function is always concave up, which means it must be concave up on this entire interval we're talking about from 1 to 5. And if you forget the rule, it's always easy enough to just sketch a little drawing and draw a couple of trapezoids. And you can see that the trapezoids go beyond the function, which means this is an overestimate. And that's about all there is to using the trapezoidal rule to approximate the area underneath the curve. And so you'll need to use this and the 3 rectangular methods on the AP test to show up in both the multiple choice and in free response every year. So that's it for today. Next time, we're going to talk a little bit about summation notation or sigma notation. And we're going to then apply that and some of these approximation methods that we've done to really figure out how integrals actually work and how to find exact values for area under the curve. But that's it for now.